So what exactly is happening with the red colored slopes over here, where we see it's concave down? Concave down on this side of A. All right. It looks like, even though it has positive slopes, and it has negative slopes, and a zero slope right here where there's relative max, there's all different types of slopes. But one thing you could say for sure is that the slopes are decreasing. If you look at the slope here, it's rather steep. It becomes less steep, so that is less positive, down to 0, right, unsigned, and then starts going negative and more negative. So therefore, we could say that the slopes are decreasing in a concave down situation. Slopes decrease. Over here we have concave up to the right of A. What's happening with the slopes? As we move from left to right, we've got negative slopes, but then they become less negative, heading towards 0 right here at the local min, and then they become more positive until they get steeper and steeper and become more and more positive. So on this side, the blue slopes, we could say the slopes are increasing in value. Okay, here comes the small leap. If the slope is decreasing, right, that would mean that f prime of x is not negative or positive per se. We saw it had positive values and negative values and zero values. The important thing is that f prime of x is decreasing, right, whenever you have a concave down structure. And over here, the slopes are increasing, so that means f prime is increasing. Not that it's positive or negative per se, just that it's getting larger, right? Negative to 0 to positives, larger positives, and so forth, as you look from left to right. If f prime is decreasing, right, we know that when a function is decreasing, its derivative is negative. So now if we just move one step up, and we look at this as being the function we're talking about, f prime is the function we're talking about. If f prime is decreasing, then f prime's derivative must be negative. If we look at f prime over here as increasing, whenever a function, even though this is a derivative function, but any function, whenever the function is increasing, we know that its derivative must be positive. So we can now say something about concavity in terms of the second derivative of a function. If the second derivative is positive, that means that the first derivative is an increasing function. If the first derivative is an increasing function, that means the slopes are increasing. And we can see that when slopes increase on a curve, it creates a concave up geometry. Okay? So to over here, if the second derivative is negative, that means the first derivative is a decreasing function. If it's a decreasing function and it represents the slopes of the curve, the slopes must be decreasing. But when the slopes decrease along a curve, it creates a concave down geometry. Right? So now we can say if f double prime, right, the second derivative, is negative on an interval, then the original function f is concave down on that interval. And switching roles, it must be that if the second derivative is positive on an interval, then the original function f is concave up on that interval. Pretty easy to remember because you have a negative second derivative associated with downwardness, right? Now, it's downwardness of concavity. It's not that the function's decreasing. That's what the first derivative would imply. But there is some sort of downwardness associated with a negative derivative, right? But this time, the second derivative, the downwardness is the concave downwardness, the geometric structure of the curve, right, is concave down. And so too, when the second derivative is positive, you have an upwardness concept going on. It's not that the function is moving up per se, it doesn't have to do that, but the structure of the curve is a concave up sort of curve.